Hey, okay, so we're on to the last part of the course. So, in the first part of the course, we discuss models of computation, namely what types of machines could solve which problems. So, we started with the simplest machines and we worked our way up to the most complex computing machine that we know of. Then we discussed efficient algorithm design, namely, we looked at a bunch of different algorithmic techniques, recursion, dynamic programming, graph algorithms, and the like. And we talked about how we might solve these problems, how we might use those techniques to solve certain problems. Next, this last part of the course, we're going to be discussing harder problems, problems that likely are unlikely to have algorithms that could solve it at all, or if they are solvable, let's say if they are solvable using brute force, they're unlikely to have efficient algorithms. Okay, so those are so now we're at the last part of the course. We want to show that hard problems are hard, and the way we show that is via reductions. So So remember that from the first part of the course that Turing machines defined a machine, a model of computation, and the Turing thesis is very simple. Any function that is computable can be computed by a Turing machine. So the efficient Church-Turing thesis is that any function that is computable can be computed by Turing machines with only a polynomial time slowdown. Okay, so this leads to two questions, right? What functions can and cannot be computed by Turing machines? That is the functions that can and cannot be decidable. And what functions slash problems cannot be solved efficiently? That leads to the problems that, as we'll discuss, are in NP. So, why do we care about this? Why do we care about anything? It's because these are foundational topics in computer science, and that's sort of what you're in school for. Um, but also, from a more pragmatic standpoint, we want to know, can we solve our problem or not? Or if a problem seems really hard, is it that simply that we're not being clever, or is it that the problem actually is hard? So having reductions at our tool, being able to show one problem is just as hard as another, could save us a lot of time. So the general the general idea behind using a problem to show hardness is to start with a hard problem, somehow x, and reduce it to your favorite problem y, right? Because what do we do? What does a reduction look like? A reduction looks like something along the lines of, if we have a reduction looks like something, a reduction looks like we want to solve a problem x, so we insert in the algorithm for y and do some jiggering to the inputs and then get some jiggering to the outputs, right? That's what a reduction does. Now, let's say we know that x is a hard problem. What if we know x is a hard problem, and then we can show that we could turn x into a problem y? What does that show? Well, if x is a hard problem, and we know we could turn x, we could reduce it to another problem y, then by definition that must mean that y is also a hard problem, right? Because in order to solve y, if y was easy, then x should be easy too, because we're reducing x to y. So that's the idea behind reductions. We're going to use sort of an initial hard problem to give us a gauge to show that this new problem that we're unsure of is also hard. On the other hand, we could also prove a problem is easy by using reductions. If, for instance, we know y is easy, we have an efficient algorithm for y, then if we reduce x to y, that means that x must be easy too. Okay, so starting off with a problem of known hardness and then showing another problem is similar in hardness to this known problem, then that'll give us a good chance to see what problems are easy and what problems are hard. And the question is, who gives the initial problem? Who gives the initial hard problem? And the truth is, it's probably just some famous computer scientists that you've already heard of. Consor, Gödel, Turing, Cook, Levin. I mean, these are the famous guys you've heard for. But there's a whole army of computer scientists that have been working on hard problems for decades. So there's quite a huge library of hard problems and a huge library of easy problems that you could use for reductions to show that the specific problem variety you were given is easy or hard. The other option is that you could assume a problem is hard because you haven't been able to solve it, even though it hasn't necessarily been proven hard yet. Okay, so a lot of problems in NP, for instance, integer factorization, that's been a cornerstone of cryptography for a long time. Integer factorization has never been proven to be NP complete. It's an NP because we know we could solve it through brute force, but no one's ever proven that it's NP complete. Still, I mean, given the likelihood of, given the fact that people have been working on that problem for decades, maybe more than decades, maybe hundreds of years, if you count number theory, if you count the earliest mathematicians playing with number theory, given the fact that people have been working on it for such a long time and there's been no efficient algorithm, pretty succinctly hints at the fact that there might not ever be an efficient algorithm, right? It's like mining for gold. If you keep digging somewhere and you're not finding gold and you keep digging in that place for decades and decades, then the probability is that there's no gold there, right? So this isn't perfect. And of course, the major drawback is that it leads to conditional results, i.e., as long as this problem is unsolved, as long as we assume this problem is hard, then that's what your proof is based on. It's not on concrete grounds, but if there's no other option, there's no other option, right? So that's the other way to prove. So what if we want to prove a problem is easy? And we actually just discussed this, that if we have a problem, let's say y is easy, then it has some polynomial time algorithm ay that runs in O of n to the k. Then what do? We just envelop that into the algorithm of x. And then we could do whatever. And then x is easy by that standpoint, right? X is easy. So if we want to prove something is easy, we simply reduce a unknown problem to a known easy problem. On the other hand, if we want to prove something is hard, we reduce a known hard problem to a unknown problem. Okay? So y gives the upper bound of easy or hardness, and x gives a lower bound of easy or hardness, right? So the major thing to remember is that if we have a scale of hardness, for this reduction here, this reduction, or actually, this line shows hardness, right? Okay? And so this line would be y, and this line would be x, right? So if x is a hard problem, let's say x is a hard problem, then we know it is a hard problem. Then we know y also has to be a hard problem, right? But if x is an easy problem, then y doesn't necessarily have to be easy. X could be an easy problem and y could be a very hard problem, right? So So just because, so you have to remember your reduction direction intimately. Okay, you have to either, to show something is easy or to show something is hard, you have to first start out with a hard problem and reduce that hard problem to another unknown problem, or to prove something is easy, you have to first show that you have to have an easy problem. So you have to reduce a unknown problem to a known easy problem. Okay, that's the big thing here. Okay, I hope that makes sense. So remember the reduction directions, and we're going to practice that more throughout the lecture. Okay, but just keep this in mind.